Welcome to Omni, where we explore nature's ultimate engineering marvels. Today, we uncover the deadly multiple sensor algorithms of the mosquito. Despite their extremely tiny size, these creatures are not simple insects. They function as highly sophisticated, biological, autonomous, target-seeking drone machines. In this 24th episode, we will deeply analyze how a mosquito hunts its prey, using an incredibly complex biological tracking system. They do not merely rely on basic vision to find you. They combine visual data with advanced thermal and chemical tracking capabilities. This remarkable integration of different data streams represents the absolute pinnacle of what engineers call sensor fusion in modern artificial intelligence systems. To truly understand this biological marvel, we must first look at the incredible anatomy of a mosquito hunting in the dark night. When the sun goes down, the female mosquito begins her desperate search for the vital blood she needs to develop her eggs. She launches into the air with a specific mission. Her tiny brain immediately activates a terrifyingly efficient array of specialized hunting sensors. Her primary objective is to locate a warm-blooded host hidden somewhere within a massive and completely unpredictable natural outdoor environment today. How does she find you across a crowded room or a dark forest without bumping into obstacles or losing her designated target? The secret lies in a brilliant combination of distinct sensory inputs working together in perfect harmony within her microscopic neural processing center. Let us begin by examining the complex visual system of the mosquito. Their compound eyes are completely different from human visual organs. Mosquito vision is notoriously low resolution. They cannot see fine details or read text, but they are incredibly sensitive to movement patterns. Their eyes are specifically designed to detect high-contrast shapes against the horizon. A dark silhouette against the sky is instantly recognized. When you walk through a garden, your moving dark shape creates a visual anomaly that immediately triggers the first phase of hunting. However, vision alone is not enough to confirm a target. A moving shadow could just be a dark tree branch swaying gently. To avoid wasting precious energy on a false target, the mosquito must cross-reference her visual data with another entirely different sensor. This is where her incredibly sensitive olfactory system comes into play. She uses her specialized antennae to detect invisible chemicals floating nearby. Every time you exhale, you release a massive plume of carbon dioxide into the surrounding air. This gas is an invisible beacon. The mosquito can detect carbon dioxide from up to 50 meters away. It acts as a long-range chemical radar for her. When her sensors pick up the carbon dioxide plume, she immediately alters her flight path to fly upwind towards the chemical source. This behavior is a perfect example of biological programming. The chemical signal confirms that the moving shape she saw is actually alive, but the wind can be highly unpredictable. The carbon dioxide plume often breaks apart into scattered, invisible clouds floating in the breeze. To navigate this chaotic chemical landscape, the mosquito uses a brilliant search algorithm. She flies in a rapid, horizontal, zigzag flight pattern. Whenever she loses the carbon dioxide trail, she instantly widens her flight path until she successfully intersects the invisible chemical plume again. This dynamic tracking method ensures she constantly moves closer to the host, even when the environmental conditions are constantly shifting and changing. Now she is within a few meters of you. Her visual sensors and her chemical sensors have successfully guided her this far, but a human body is large, and she needs to find the absolute perfect spot to land and extract her blood meal. At this critical, close range, a third, highly specialized sensor is activated. The mosquito begins to detect the body heat you radiate. Her thermal sensors can pinpoint the exact locations where your warm blood is flowing closest to the surface of your exposed skin. This thermal imaging capability allows her to avoid thick clothing and target the most vulnerable areas of your body with absolute precision. Imagine looking through a military-grade infrared camera. The mosquito sees a glowing map of heat signatures guiding her final landing approach. In addition to heat, she can also detect the specific moisture and sweat evaporating off your skin as she gets extremely close. Certain body odors and lactic acid compounds act as the final confirmation signal. Her biological targeting sequence is now absolutely perfectly complete. This astonishing sequence of events relies on the seamless integration of visual tracking, chemical detection, and precise thermal imaging in real time. Engineers refer to this exact process as sensor fusion. It is a critical concept in the development of modern autonomous robotic systems. A self-driving car cannot rely solely on a single camera to safely navigate through a busy city street full of obstacles. Cameras can easily be blinded by bright sunlight or heavy rain. They require additional sensor layers to guarantee absolute safety and reliability. Therefore, engineers equip autonomous vehicles with multiple overlapping sensor systems, including laser-based radar scanners and high-frequency ultrasonic proximity detection units. The central computer of the car acts as the brain, continuously merging all these different data streams into one comprehensive environmental map. When the camera sees a shape, the radar confirms its distance, and the laser scanner builds a highly detailed three-dimensional model. This multi-layered approach ensures that if one sensor fails or provides false data, the other sensors can instantly compensate and correct. The Mosquito has been perfectly executing this exact same multi-layered sensor fusion algorithm for millions of years of brutal evolutionary history. Her microscopic brain contains fewer than 300,000 neurons, yet it processes complex multimodal sensory data faster than many modern computers. She effortlessly combines the low-resolution visual shape data with the long-range chemical tracking and the short-range thermal targeting information. If you hold your breath to stop emitting carbon dioxide, her visual and thermal sensors will still guide her directly towards you. If you hide in the dark to defeat her vision, her chemical and thermal sensors will easily track your invisible biological signature. It is an incredibly robust and redundant targeting system. It is almost impossible to completely hide from a highly motivated, hungry mosquito. This is precisely why mosquitoes are considered the most dangerous and successful hunters on the entire planet, responsible for millions of deaths. By studying how the mosquito brain integrates these diverse sensory inputs, scientists are learning how to build vastly superior artificial intelligence systems. Imagine a security drone equipped with the Mosquito-inspired sensor fusion algorithm. It would be virtually impossible for any intruder to escape. The drone would visually spot the intruder, track their carbon dioxide emissions, and pinpoint their exact thermal signature hidden in the bushes. This level of inescapable surveillance is the ultimate goal for many advanced military and private security robotics development programs around the world. Furthermore, understanding this biological sensor fusion is helping researchers develop highly targeted traps to control dangerous mosquito populations in tropical disease zones. By artificially replicating the exact combination of visual contrast, carbon dioxide, and heat, scientists can build the ultimate, irresistible, deadly mosquito trap. These advanced traps trick the mosquito sensory fusion algorithms, causing them to confidently land on a deadly surface instead of a human. Nature has provided us with a perfect blueprint for multi-sensory integration. We just need to decode the secrets of their biology. The architecture of the mosquito brain is a masterclass in extreme efficiency and optimized data processing under severe energy and space constraints. Unlike massive server farms that consume megawatts of power, the mosquito brain runs its complex fusion algorithms on a tiny energy fraction. Researchers are now developing neuromorphic computer chips that mimic this exact biological efficiency to power the next generation of tiny autonomous robots. These incredibly small robots could be deployed in disaster zones to search for trapped survivors using their own advanced sensor fusion arrays. They would sniff out the carbon dioxide of breathing victims while using thermal cameras to locate their warm bodies under heavy rubble. This is the beautiful irony of science. The world's most annoying and deadly insect might inspire the technology that saves countless lives. Let us look deeper into the exact moment of the mosquito strike. The final landing approach is a marvel of aerodynamic control. As she closes the final few centimeters, her vision becomes less important. Her thermal and chemical sensors take complete control of navigation. She extends her delicate landing gear, feeling the microscopic air currents shifting around your warm body to ensure a perfectly silent touchdown. Once she lands, her proboscis acts as a final, incredibly precise tactile and chemical sensor to locate the absolute best blood vessel. She probes the skin, detecting the exact chemical composition of the blood beneath the surface before committing to the final deep bite. This entire hunting sequence, from the initial long-range visual detection to the final microscopic chemical analysis, is a continuous, unbroken algorithm. It is a terrifyingly beautiful symphony of sensory data processing. Every single environmental input is analyzed, weighed, and acted upon almost instantly. The speed at which her tiny brain processes this massive amount of multimodal data is something human engineers can only dream of. In traditional robotics, processing distinct data streams from cameras, radars, and chemical sensors requires massive computing power and incredibly complex software architecture. The data must be synchronized, calibrated, and filtered to prevent the robotic brain from becoming completely overwhelmed by conflicting environmental noise signals. Yet the Mosquito handles this immense data load effortlessly while simultaneously controlling her complex flight muscles and navigating unpredictable turbulent wind currents. The biological secret lies in parallel processing. Different regions of her tiny brain handle different sensory inputs simultaneously, without any noticeable processing delay. When the visual cortex detects a moving shadow, it instantly primes the olfactory center to be highly sensitive to carbon dioxide molecules. The sensors do not just work independently. They actively communicate and enhance each other, creating a holistic perception of the surrounding environment. This cross-sensory enhancement is the true genius of biological sensor fusion. It allows animals to make incredibly fast and highly accurate decisions. As we continue to push the boundaries of artificial intelligence, we must look beyond simply increasing raw processing power and memory capacity. We must learn to design intelligent systems that can elegantly blend multiple streams of perception into a single, unified understanding of physical reality. The Mosquito teaches us that true intelligence is not just about seeing the world. It is about feeling, smelling, and truly experiencing it. A machine that only sees is easily fooled. A machine that sees smells and feels the heat is an unstoppable autonomous force. By studying the microscopic neural pathways of this common pest, we are unlocking the foundational principles of advanced robotic perception and artificial cognition. The next time a mosquito buzzes near your ear, remember that you are being targeted by a masterpiece of brilliant evolutionary engineering design. You are not just fighting a simple flying bug. You are trying to evade a highly optimized biological sensor fusion tracking drone system. Beating this system requires understanding its complex, multi-layered nature. You must disrupt its vision, its smell, and its advanced thermal tracking abilities. Wearing light-colored clothing reduces your visual contrast. Using strong chemical repellents effectively blinds her sensitive carbon dioxide and specific odor sensors. Staying in a cool environment or using a fan disrupts the thermal and chemical plumes, making it incredibly difficult for her precise tracking. It takes a multi-layered defense strategy to successfully defeat a multi-layered offensive sensor fusion hunting algorithm in the real physical world. The ongoing arms race between human technology and mosquito biology is one of the most fascinating battles in the modern advanced scientific world. Every new discovery about their sensory capabilities brings us one step closer to eliminating the deadly diseases they transmit across the entire globe. At the same time, these amazing biological discoveries are directly fueling the rapid advancement of our most cutting-edge artificial intelligence robotic technologies. From the darkest jungles to the brightest robotics laboratories, the humble mosquito is unknowingly shaping the future of human technological innovation everywhere. Today, we are slowly learning to replicate the elegant perfection of nature. The fusion of multiple sensors is the key to true robotic autonomy. Soon we will have incredible robotic assistants that navigate our complex world with the same effortless grace and precision as advanced natural organisms. These advanced machines will seamlessly integrate visual, thermal, and chemical data to perform incredibly complex tasks in highly unpredictable and dangerous outdoor environments. The biological algorithms developed over millions of years of brutal evolution are now becoming the foundational software for our future robotic autonomous companions. It is a profound realization that the key to building the smartest artificial machines lies hidden within the brains of tiny flying insects. The natural world is an infinite library of brilliant engineering solutions waiting to be discovered, analyzed, and replicated by curious, advanced human minds. The mosquito sensor fusion algorithm is just one small chapter in this massive, incredible book of biological wonders and advanced natural evolutionary technology. As we conclude this deep dive into the fascinating world of biological sensor fusion, we hope you have gained a completely new perspective. The tiny mosquito is a perfect example of how combining simple sensory inputs can create an incredibly powerful and unstoppable biological hunting machine. We will continue to explore these amazing connections between the natural world and advanced artificial intelligence in our future scientific documentary educational videos. Thank you for joining us on this incredible journey through the microscopic neural pathways and advanced hunting strategies of the common deadly mosquito. This has been another exciting episode of Omni Eyes. Stay curious, keep exploring, and we will definitely see you in the next adventure.